What's up, everyone? This is our presentation on an air fryer.
A little bit about the product itself. We decided to go with the standard countertop air fryer as it was something we're all familiar with and used in our day-to-day lives. We felt that this would help give us a better perspective on the types of functionalities we'd want to include in the design from a customer perspective, but also a better understanding from a technical perspective related to things like manufacturability and assembly. Air fryers are a versatile and healthy alternative to deep frying with use of little or no oil. They also have a wide range of applications which had to be maintained in our design. We also took consideration of the hot air circulation technology within the air fryers in deciding what components were essential versus non-essential to carry out normal operation.
So for the production volume, we have an average of 85 million based on this chart that we found on Market US News. So taking a look at our account here, we have our primary customers and our secondary customers. Looking over at the explode view, you can see all the different kind of parts that we have. So basket, grill, heating element, fan, a couple sensors, some buttons to start it, the wires that take that information, a PCB board, and this is all fastened together. Looking at our primary customers, we have household users that want quick and convenient food. That's a little bit healthier, and we see that this is 60% of our customer base. And our secondary customers will be chefs who want higher quality food at larger quantities.
The functional analysis is presented in the slide. The task function is to cook the food. To do this, we must apply heat, circulate air, and contain the food. We also have to assure dependability by preventing burns and electrocution to the user. We need to assure convenience to the user by accepting inputs so the user can cook the food however they desire and display the input so the user knows what the machine will do when they start it. We have to also enhance the aesthetics of the machine and dampen the noise of the air fryer so the air fryer is pleasing to the senses of the user. The assembly fishbone diagram is shown here in sequence 1. We see that the housing and the screen are assembled first, then the PCB and the fan are two sub-assemblies that are assembled externally, and then eventually assembled into the housing. And then finally, the door sensor, the bottom housing, and the basket are all assembled to make the air fryer assembly. Whereas in sequence 2, everything is getting assembled sequentially and not externally separate from each other, where the PCB will be assembled into the housing, and then the fan, and then the door sensor, and so on and so forth, where we see that the fan and the heat element, instead of being a module, they're assembled into the housing one by one. When we compare the sequence, we see that sequence 1 is overall better than sequence 2. However, sequence 2 does a few things a little bit better than sequence 1. For example, the parts are easier to transfer and handle since there is not as many reorientations of the subassembly needed to assemble all the components. Similarly, to locate the parts, the assembly is going to be in the same location and no unique locators are needed to assemble all the components, whereas in sequence 1, some unique locators might be needed. However, in sequence 1, since things are getting assembled in parallel, that also makes subassemblies easier to test on their own, especially the PCB and the fan. The function component mapping matrix is presented. As we see, each function is satisfied by at least one component, and some functions are satisfied by more than one component. For example, preventing burns. The housing and the bottom housing and the door sensor must work together to prevent the user from getting burned.
So here we will cover the BOM for household variant and commercial variant of the air fryer. The household variant focuses on affordability and simplicity with a single heating system, while the commercial variant includes dual heating system, dual fans, larger basket for faster cooking and high performance. The estimated manufacturing process, assembly method, and production cost for each component. The household variant had an estimated unit cost of $58, which is around 58% of the retail price, while the commercial variant has a cost about $128, which is around 50% of the retail price. Both designs are considered manufacturable and economically feasible, and we also identified opportunities for cost reduction through improved assembly sequencing, modular design, and reduced part complexity by sharing multiple parts between both variants.
Taking a look at the quad chart for the household variant of the air fryer, it's clear that a lot of design changes could be made for the sake of manufacturability and ease of assembly. These changes could also help save time and money. Some of the things that stand out to me are the screen, which we placed as low importance but at high cost. Making a sacrifice like removing the screen and switching to something more digital could help us save money while also maintaining the same standard operation. Some features like the housing and basket are of high importance but also high cost. I think that this calls for some redesign in the materials we choose to use, but also the way we assemble the product. Looking at the quad chart for the commercial variant, the same approach to analyzing the chart was maintained. Similar to the household variant, this also calls for some redesign. Things like the screen or removable grill were placed at a high cost and low importance, which could be eliminated completely or rethought in our design to help save time and money.
For the functional differentiation table, we relied on the leaves of our FAST diagram to determine common and different functions for each customer group. The common functions are similar for both since we needed to have the same safety and usability for both products. We found that there are many functions that we can classify to be different for each group since our goal was to create a commercial version that has a larger capacity for storing and containing food, a higher power for supporting 2 fans and different user controls, while the primary version prioritized having a quieter option. For component commonality table, we used FDT and the function component mapping matrix to determine the platform and the module components. The platform components, like housing, screen, plug, door sensors, are shared across both products. By keeping those parts common, we are reducing the manufacturing cost. The module components included a larger basket and bottom housing for the secondary customer group, with 2 fans that runs faster and 2 PCB for zoned heating, higher number of knobs, removable grills, and also NTC thermal sensors for the commercial group, which is double the amount of elements.
The original assembly sequence is presented in the slide. The product deviation happens earlier in the original sequence because the PCB is assembled ahead of a lot of the other components, which results in the 2 product lines separating earlier in the sequence. However, in the modified assembly sequence presented below, we move the plug, the screen, and the door sensor, which are common components, ahead of the other components, and that makes the deviation happen later in the product line.